I'm going to go grab something cold to drink. I shall return. Grab something cold to drink. I shall return.
Somebody's watched the YouTube video on delay.
That's me, Michael. I just muted that.
I did that all the time when I was live streaming my lessons on YouTube. But I would actually have it like I was afraid sometimes it would kick out. So I had like one student every once in a while just turn it on so I could hear the echo and then turn it off.
Oh, nice.
Michael, where are you located?
I'm in Connecticut.
Oh.
You said you're in Newington. Do you visit the ARRL headquarters ever?
I do. I did this one workshop back in 2017 with Alan and Tommy.
Oh, awesome.
Other people. I recognized like Alan, but I couldn't quite place it. And then I'm nerdy enough. I'm going to do my little fake pushing my glasses up on my nose. I wrote everyone's name down in my notes. And I went back to the notes during the middle of our last meeting to remember that Alan was there.
Yeah, that was great. It was a bummer because then, we did that and we applied for T2. I wasn't selected for T2, which is a really cool next level, getting into working with communicating and ham and being able to send out and grab remote data through connections to the ham radio and things like floating out on a lake or on the ocean or whatever. And then applied again for T2, COVID hit. And so I've just been in this waiting mode, but yeah, the T1 class was great. And when I saw what they did in T2, I just pretty much started drooling. And I knew nothing about ham radio. I mean, I could spell it, that was about it. And Wednesday night, I studied for the first time. And Friday, I took the test and I got my, whatever your first level ham.
Technician, yeah. Tommy's predecessor, I sat in on their workshop. It was the second one they ever did. And Tommy's predecessor basically said, yeah, we'll be having a test at the end of this for anybody who wants to get their license. And Andy will be taking the test. And I'm like, what?
Yeah, it was pretty cool. So I got a customized call sign. Is it Kilo Nora 6 Hotel Oscar Golf?
Okay, so I don't remember my call sign.
Well, I did hog because of ham and then hog because I ride a Harley.
Ah, okay. Yeah, I went on and got my GROL. That's the general radio operator's license. That's not part of the amateur system. That's for, say, use on ships and other commercial applications. The ham radio is a great segue into it. And there's a lot of there's significant job opportunities with the GROL, and so I recommend teachers get familiar with amateur radio and introduce it in their classroom, because there are career paths associated with it that are in the electronics field.
Yeah, I found I was interested in trying to look at something like that with middle school, but as a general class, that's really tough. You just don't have the intrinsic motivation.
Yeah, I can completely see that. All right, let's get started. So here we are back at day 2 of What's a Microcontroller with Python and the Microbit version 2.0. I'm Andy, and on day 1, we did some overview stuff and then basically put our kit together and built a first circuit that was just a DC light emitting diode circuit. And then I sent out some homework, and that homework we'll get to in a little bit. It had to do with building a circuit that's going to encompass the next couple of chapters in terms of the activities. It makes it so that we can do a fast forward version. And am I not screen sharing? Have I just been pointing at the slides?
Yeah.
Yes.
It's just
All right.
you.
Just me. Okay, so here we are. And now you can see that I was talking about, we did some overview stuff. We put together our kit, tested some continuity, built a DC light circuit. And then for homework, that's where I had you guys build some circuits and then try a few of a very pared down version of what I called out during the previous session, where first I had you build up circuits to encompass the next two chapters, and then also, let's see, try a few activities within the LED lights chapter. Folks, how did that go? Can I get some thumbs up, especially on the Cyberscope connection? Were you guys able to all make that work? It's a very brand new thing, so I'm curious here.
It's very cool.
I'm glad to hear that. Yeah, so I know Ed and Alan got it going. Ooh, looking good, Neil. Yeah, so like I said, there were three things actually. There was battery holder plus batteries. Then there was build a master circuit for the next two chapters. And then there were a few select activities within the lights chapter. And we're going to take a closer look today. So what are we doing today? Basically, we're going to, I did skip a few things on Monday, and I'm going to go quickly through those in terms of just showing you a few things that we didn't go through so that you know they're there. And after that, since we've got all our circuits out, we'll try push buttons, LED lights, and if time permits, we're going to build the servo and run that too. How's that sound?
Cool.
Okay, and as we go, we'll be testing, we'll be building and testing this stuff with the Cyberscope like we would with normal test equipment. So I've got somebody coming through who has sound in the background. Hopefully they already self-muted. Okay, so that's where we're going today. Oh, no, I've still got interference on the, okay, hopefully now there.
Yeah, this is Mark Evans. I'm stuck in traffic in Chicago. I'm not going to make the meeting. I just wanted to tell you that. I will try to zoom in later.
Okay, thank you, Mark. And also we'll be posting YouTube recordings of all this.
Thank you.
Certainly.
Thank you. I apologize. I had to drive my wife to the airport.
Oh,
Can you
please.
can you guys mute me and I'll listen?
Okay, that was Mark Evans.
Yeah, we got you.
Yes.
And in
thank
fact,
you.
how about if we grab one of the teachers here to be a co-host for muting purposes, Andy?
That sounds good. Who wants to volunteer? Who's a good Zoom co-host that's had experience?
Help out.
I can help if you like.
Okay, Michael, I'll assign it to you right now.
Good idea, Ken.
Okay, Michael's there. He'll help you out.
All righty.
Thanks, guys.
Okay, so we stopped at first breadboard circuit, and the specific spot that we stopped at, we stopped to test the supply rails, really. Tell me if this looks familiar. So we were testing to make sure we had 3 volts
Yep.
on the supply rails. Let's see if I can get to remember we had the voltmeter display. Now, one thing I wanted to bring to your attention is that if you've downloaded that voltmeter display, you can, in this, we're duplicating it and then commenting out the terminal version. And then in place of terminal, you can type in Cyberscope, and capitalization doesn't actually matter. And then when you run it, you can basically, here we are flashing it. Then you can go over to the Cyberscope and, whoa, sorry, you got to disconnect, then go to the Cyberscope, and then you can connect. And the newer one should automatically tell you what, switch you over to the voltmeter, but there you would see it as a voltmeter style display. And that is one of the main goals here, is that students get the experience of using equipment without classrooms necessarily having to set up a lab that has a voltmeter, function generator, oscilloscope, all those other things that you would normally use to look more closely and understand circuits better. So, so that's a thing that we'll be using today, and that hopefully you had a chance to try out. Okay. Let's try to keep the number of tabs to a minimum here. All right. Next thing I wanted to talk with you about was just the first breadboard circuit. Just wanted to let you know that here it is. I think we did this. I think we connected an LED and then we measured from the positive rail to the negative rail and noticed that it didn't change. The main thing that I wanted to point out with this LED is they're going to build this DC LED and they're going to measure it. So they're testing the LED circuit. So the main thing here is just basically plugging it in and making sure that it turns on. But we talk about things like how the circuit works. So we introduce the different parts and how they work together and explain it. We talk about resistor color codes and how current flows, and how essentially the electrons are actually coming out of the negative terminal of the battery and flowing through this way. But in most schematics and circuit diagrams, current is considered to be opposite the flow of electrons. And so positive current flow goes from higher voltage to lower voltage normally. Last, we had to try to drive home the point of current flow. We took a resistor, which is something that resists the flow of current. We took out this relatively small 220 ohm resistor and replaced it with one that's roughly 4 times that size, a 1 kilo ohm or 1000 ohm resistor, and observed that with less current, the light is less bright. Please do feel free to jump in with any questions as we go. All right, some things I wanted to talk to you about in the electrical measurements chapter. That's the next chapter. I'll just bring it up so you can see the cover page real quick. All right, so here is the cover page of electrical measurements. And in electrical measurements, we measure voltage, resistance, talk about measurement units, then we measure current, and then talk about Ohm's law. So I try to kind of split it up between measuring and theory and hand calculations and writing scripts. Okay, script and tests. All right, so it's best to have your students download the pre-written scripts for cyberscope measurement, because it has incorporated into it a module that if you just fire up the editor and type in the code, it won't have that module, and so it won't work. But when you download a hex file, as would happen if I right click here and select save link as, it's going to come up and say, hey, do you want to save this hex file? And I can say yes and save it. And then it'll essentially be ready to open in the python.microbit org editor. And again, that's where you load it into the microbit, then disconnect, and then go to Cyberscope and hit connect. So for example, I might as well go through that right now. All right, so I just downloaded measure volts. Now we'll go to python.microbit.org and then do that open the code routine thing we did yesterday. So I just hit load save, and then I'm going to drag the code I downloaded and drop it into the gray box and load. And here we are with this time voltmeter is terminal display as commented out, and we're going to display it with the Cyberscope. Then connect, discover that I haven't plugged in the Microbit yet. All right, let's try it again. Connect, choose your Microbit, hit connect, flash the code into the Microbit. Okay, here is an optional step. Whoops. The optional step I was talking about was not to load it into the Microbit a second time. The optional step is to look at Open Serial, because you can actually see the values that are currently being sent that are intended for the cyberscope. So this is not intended to be human readable, but as you can see, there's a V in quotes next to a voltage measurement. And then the large number next to X is actually the time measurement for whenever we use the oscilloscope. All right, anyway, it's normally load save to get the thingy downloaded, flash, and then disconnect. Okay, then the instructions say, okay, now that you're disconnected, go to Cyberscope and click connect. So when I go to Cyberscope and click connect, you got to make sure to pick out your port. I have some other ports that are, like it's definitely not a Bluetooth. You want to look for embed serial port if it shows other options. Usually there's only one option, and so embed serial port is a cue that's your Microbit. When I hit connect, because the device is auto, notice that it automatically displays the voltage. And I don't currently have it connected in the right way to measure that 3 volts. I'm now fussing with my voltmeter probes. There we are, 3.3 volts. Okay, so that is that gives students a little taste of taking measurements with an oscilloscope. And it's very important to know these steps. And also, although it is somewhat forgiving, like for example, you'll find that students run over here, they click connect, and they'll flash the next program. And because of the fact that I'm still connected here with the cyberscope, if I try to view that serial data again, notice there's just a bunch of, not very much and not very intelligible. So that is something that if they try to view this, the serial port, so I'm going to close serial, but we're still, so that the basic idea is, yes, you can flash new code while your cyberscope is connected, but really overall best practice is when you're done with something, disconnect it. So right now I'm disconnected. So my cyberscope, I have a connect option. Over here, I'm also disconnected. And that way we can be confident that nothing's going to try to take over that communication port. If you always try to keep whatever you're not using disconnected, it'll be a better experience. All righty. So what do we have next? So I wanted to point out that I saw the practice solutions and I was going to talk about that. But oh yes. Okay. So after taking those measurements, and we take more than just the, like if we go back to the tests, let's take a look at where the measurements are actually taken. So you see we're measuring across the entire LED circuit. Then we're measuring the voltage across just the resistor. And after that, we're measuring the voltage across just the LED. And the instructions are saying to record those. Okay, so then we go to how it works. And what how it works talks about is one of the laws of electronics. It's called Kirchhoff's voltage law, or KVL, as electronics nerds affectionately refer to it. And what it says basically is if you have a loop that current is passing through, your increase in voltage across the battery has to add up to the decreases in voltage across the loads that are in that same loop. And so that is something that we introduce here. That is, again, we're doing a little bit more engineering-esque, a little bit more thinking inside the circuit. So next up is practice stuff. Now,
Can you go back
yes.
to that for 1 second? And just looking at the mathematics is that sort of like there's no loss, but I see 2.05 and 1.15, which come up to 3.2.
Oh, no. Thanks for catching that. I need to bear with me a second. I'm going to open up my my notes here.
Okay.
And
So I took my shoes off to count this twice.
well, yeah, I think that was the problem, is I was wearing shoes and mittens while I was typing, and so I had no way
See,
to
I
do
read it and I said, well, it's because you're going to measure like 3.25 at one point, and you're going to have a little bit of loss through the conductors. Okay, that
Exactly.
makes sense. Like
You
I
know,
knew it made sense.
Michael, I was waiting for that there's some, there's a load that's being taken out by some transistor or something.
Yes, Al and I wisely did that. No, I didn't.
Well, it gets the class talking, so that's good.
It does, but this is not the place I want to get the class. Not really the way I want to get.
Yay, node analysis. Yay, node analysis.
Yeah. Let's see here. So issues, incorrect. KVL edition. All right. Good thing I wasn't working on any Mars landers. Let's see here. Okay, so that is, so after that, we, no, sorry, before that, notice that we have, we're prompting the students to try some things. And then we're also having them actually, for example, use KVL to solve some problems of what would they expect to measure if they see two of three quantities where the third is unknown. And these are always half of the questions, exercises, and projects, or less. And you will see the rest of the questions, exercises, and projects for a given activity, that being like, here we are for this activity, and then this activity and this, all the rest of these activities will also have questions, exercises, and projects. And so there's half that usually appear here, and then the other half appear in the assessment materials where you can copy and paste them as homework assignments, quizzes, tests, however seems to fit your classroom the best.
Andy, two things.
Yes.
One, I have two comments that I pulled out from the reading from before. I'll email them to you afterwards, just like notes, like little mistakes.
Okay, good.
But then we had a question in chat from Delphra asking about the Mu editor, if there's any differences using the Mu Python, the Mu editor for Microbit for these hex files.
The Mu editor was not aligned with the version 2.0 for long enough that I had to leave it behind. So I actually don't know the answer to that. Let me add that to my for Friday. Okay, so prep Friday, find out about Mu editor.
Andy, one other question about the Mu editor that I have, and I was going to ask you is there a way to change where it dumps the files? Because it dumps them into a directory where I do not want the students to be.
Yeah, I agree.
I mean, it's not, it's in their directory, but it's at a level where, they can do some damage. It's not in the document directory.
So Edward,
Yeah, it's basically at the same level as the document directory, but
same
not
level.
visible.
Yeah.
Edward, there's a couple things that I do in my class, and especially because with middle schoolers, it's really difficult for them to find things. Are you under Windows or under Mac?
We're in Windows.
So under Windows, one of the very first things that I teach besides file structure and all of that is the quick links. And I have them go and just make a quick link. So what happens is under Mu, you'll go and click save. When your file menu window opens up, over on your quick access on the left, they could just select documents or section 2 or electronics. And I typically have them save most of their work in Google Drive in a particular folder, so that way they can work on things anywhere if they're absent. By using those quick access links, it's really nice. You just open it, click it, and go that way, and that works for anything.
Yeah, it's been a while. I don't even have
look at that, Alan. I had looked at it, played with the editor, to figure out because there is a block that they have where you can set things.
Yeah.
But the documentation they have is sorely lacking. And again, I just didn't, we do go over it, but that's a place where they can do too much damage too fast, and I don't have time to undo it during the class.
I'm more than happy to work with you offline and show you how to do it.
Sounds good. Sounds good.
Okay.
I'll take you up on that.
Cool.
Okay, sounds good. I also have a note to myself to check the settings for Friday in case there's a easier way, though honestly, I use the same technique that Alan did. I just put a shortcut on my quick access and then forgot about it.
Oh, I know what you're doing. Okay. Yeah. All right. Yeah, maybe. Okay.
There are also there's a hidden gear on a particular settings screen that I think might allow you to change the
If you
directory.
could figure out what's going on, I'm sorry, I think if you could figure out what's going on in that, yeah. Because there's no documentation. I can't even find it on their site.
Okay.
And the things that they fix, they're constantly fixing stuff or changing stuff, which I don't even okay, fine, All right, thank you.
Okay, sure thing. Wait a minute, maybe I'll try clicking Mu apps. Yeah, it's not coming up. Okay.
Do you want to set, I'm just curious if it's just within the browser, you want to set a different download location or default download location? Is that as simple as what you're trying to do?
Oh, it's different. You can, if that was Neil, you can go in under Chrome and
Right.
you can select a default download, but that's not the same as these files or programs like New going in and doing a load and save and just saying, this is where I want it to be. So downloads is kind of unique.
For example, when you hit files, oh, that's right. Okay, so this files on your computer lives in a Mu
Right.
folder that's at the same level as your documents. And normally, in most school setups, you can't really get above my documents. And so let's see, where is the settings?
See, I'll tell you, it's the first programming environment I've ever encountered where you cannot easily customize it.
Okay, so Ed, can you see this little gear down here?
Yes, I know where the gear is, right, and this comes up.
Okay. Wow. Okay, so override the built-in. Yeah, okay. Yeah, there may be some special thing you can add here, but geez, that's setting an environment variable. So that's not really a very graceful way to get it to
I was going to put a suggestion. I haven't had time. I was going to put a suggestion out on their website to say, this would seem to be a simple change. I would guess it'd be a simple change. I haven't looked through their code. I've got my hands in enough pie now.
Yep. Okay. So moving on to electrical measurements. That's the next chapter. Here's the cover. Oh, actually, I mislinked that. This is the cover. And it always talks about kind of a 10,000 foot view. Going into measure voltage, I'm still pretty carefully drawing pictures. I kind of
smiley face.
Hello? Okay, so we put the parts on the upper left, and notice that as I place the parts, the schematic populates. And like the resistor is sticking up, and then when you plug it in, that's when the 3.3 volts appears. And we give you a close-up to make sure that students do it accurately. There's also the MP4 version right here, so you can open it and stop it from playing at certain points. Okay. Let's see, as far as measure voltage, is there anything I want to, I mean, you guys saw me do do we have any questions about that? I'm trying to be careful of the time and not dwell too much on something. So for example, the steps are essentially the same as checking your, as the KVL measurements. So I showed you KVL measurements earlier, and then this is what we did, where they took their notes and they saw it in the cyboscope, and then they compared that to Kirchhoff's voltage law. Moving on to measure resistance. I had a question from an instructor before the start of the previous workshop day. And he said, hey, I'm using this ohm meter feature, and it's just not giving me anything but huge measurements. And I hastily set it up on my system and also got nothing but huge measurements, and was worried about what I might have changed. But for me, this 3-pin header was actually in the wrong column. And so that's why I got crazy measurements. As soon as I essentially did it per the circuit instructions. So basically adding a 3-pin header to the red column, a 2K, that's red, black, red. And then all of our resistors, the fourth bar is gold for 5%. And so you jump the resistor from ground to a row, and then you put a 3-pin header on there so that you can connect an alligator clip, and then P1 by default is where resistance is measured using the P1 pins A to D. And then moving a little bit forward, make sure your students are very careful and get everything right. If they do like I did before the workshop on Monday, then they're going to have disappointing results. Once they've checked their work, the idea is to, it doesn't really matter for resistance measurement, but I put the black clip on P1 and the red clip on the positive 3.3 volt rail here. And then you have to make sure to really impress upon your students that you cannot measure resistances in the circuit. It is discussed in the tutorial, and it is discussed in the script and tests. So here's where we show, hey, look, we took the resistor out of the circuit, we measured it, we put it in the voltmeter or in the ohm meter probes. We plugged it in the rows with the ohm meter probes. Now, most folks, you can also just use the clips of the alligator clips to grab on to the ends of the resistor. That's fair game too. I added a comment about that. But this is a very important lesson. I actually had, there was a brand new, just out of university educated engineer that I was working with. And this person said, hey, I'm not really getting the right resistance measurement here. And I looked at the circuit and noticed that the reason for that was because they had not removed the resistor from the circuit to measure it. And it's a very important rule. So that's why I harp on it here. And I want to remind all of you, if you're trying to measure resistance, remove the resistor from the circuit and isolate it. That's the only way to measure resistance.
So if you're working with a circuit board and you're trying to figure out if that's just possibly what the issue is, all you can do is look for continuity because you can't isolate that resistor. Is that true?
Okay. It's really a great question. Let's skip forward then to Ohm's law. And what Ohm's law does is it basically says you can use a little bit of math to probe voltage in a circuit. And then if you have other knowns, you can use those knowns to calculate things like
Solve
resistance. Yes. Or R in your case. So that would be this one right here. Yeah. So I'll get back to that in just a second. So we do one on measurement units, and for a number of the folks where the students are used to just loading it, running it, and being excited about that it works, this is going to be somewhat of a deeper dive. I did the best I could to include support. So here's an overview of like some of the common quantities, symbols, units, names, and explanations of what they represent in a table. Now, what I also did was tried to make it somewhat simple. So everybody's kind of familiar with kilo. So we started out with that, and kilometers, and did some calculations. And then I did a fairly careful how to take a metric prefix like K for kilo and replace it with what it represents in a way that's understandable. And I also added in the chalkboard work for doing that. And there's also some practice examples. And then at the end of the activity, there are practice and solutions, as with the rest of the activities. So it shows how you multiply something by, or divide in this case, by kilo on both sides. Kilo cancels. We have 1 equals 1,000. So that's 2 kilo ohms times 1,000 over K, which is 1. The K's cancel, and so on and so forth. And that's explained also in words up here. So I trying to make sure that you've got everything you need to get this across if you need to. Now, since we're using the microbit, why not write a script that implements that? We just did it by hand. So on the coding side, setting the electronics aside for a second, let's write a script that does those conversions for us so that you can open up your terminal and click it and then type in K and you'll get your value. And we do that converting the other direction too. And then there's measure current. Really quick thing about that is measuring current also has some special things. First of all, we're adding a 20 ohm resistor across P0 and P2. See that right there? It's going to magnify in a second. Okay, so we're adding that resistor, but only for current measurement. And then you want to make sure to take it out for all the rest, because we don't do very much current measurement. But here's an example of some current measurement. And sorry, I'm missing a diagram. Okay, here it is. I believe maybe I didn't let it finish. Okay, so we have our resistor in place, and then over here, there we go. See how we moved the ground wire over? So now the light comes off. We put the probe on a row with the ground wire and the other probe on a row with the light, and that completes the circuit again. And then essentially now the current's flowing through here, through the voltmeter, and then back. I'm actually going to open that one to make sure you can see it. Okay.
So you're using the 20 ohm resistor as a shunt resistor and measuring the voltage drop across it.
Yes, another way to think about it is we're creating a voltage divider with the 20 ohm resistor. It's not exactly the same as inside. Well, Some digital ohm meters just use an extra small resistor. Others use a magnetism trick where current flows through some coil loops, and then that causes current in a separate circuit, and which in turn can be measured. So here we are starting with, the same old light circuit that we had. And the important thing is that we're moving this wire to another row. So that opens up this circuit here. And this is standard procedure for ammeters. You always insert the ammeter into the circuit. And so we're going to connect one probe of the ammeter here and another probe here. So there's a close-up, and then there's the ammeter. Now the electrons are flowing through most of the LED circuit as normal, but before going to ground, they're going to go up the red clip through this small 20 ohm resistor, back out the black clip, and then finally to ground. And the idea is that this is just a cute trick that we can use to allow the microbit to behave like an ammeter. Hope you like it. I was very pleased that it all worked out. It is a little bit tricky. Like, you don't have a wide range. You really have about 100 to 10,000 ohms of kind of meh precision with a 20 ohm resistor. But just to have the experience of measuring current and knowing that you have to do something different from voltage and resistance in the way you measure it is helpful, I think. Okay, then back to Ohm's law. We introduce it. We take some measurements. We do a script to make the conversions. And then we also talk about a real life situation. Oh, first of all, I show how to get, if you only remember V equals I times R, you can use a little bit of algebra to get the other three variations. And after that, there's some examples of hey, let's see. There are some examples of if you want to make your LED the brightest it can be, and you're limited to 20 milliamps for that LED, how would you use Ohm's law to calculate the resistor you could really use to get that done, or the resistance value you would need, since 60 ohm resistors aren't all that common. Okay, any questions before we move on to the next chapter? Shall I take silence as assent?
Tacit acceptance.
Oh, I just hope it's not resigned acceptance. Okay, so LED lights, let's have some fun. I know there's comments coming through on the chats, and I'm having trouble tracking those while presenting. Can our moderator just kind of give me a heads up if any questions come through that I might want to try to answer?
No, the other thing that came up since the last time I interjected was a comment about the floating values that you can get through if you don't isolate the resistor, or if you're measuring, you don't have the actual voltage connected. It may still come up with values even though nothing's connected there.
Yeah, and it's because it's not an expensive, high quality voltmeter. It's just a $20 microbit and an application thereof. So it's not going to be identical in every way, but I'm trying to get as much as I can so that students can have had the experience once before they end up in a lab later. All right, so we did connect and blink a light as homework. And so I just wanted to check and make sure that everybody was able to basically get through the light blinking part. Oh, shoot. I had a great suggestion to change my camera to 60 Hertz and I forgot to do that. Shucks. Well, so I'll basically describe what I see for now. So here was the light blinking. And did everybody succeed with that? I hope so.
Yes.
All right. Okay, so once we get the light to blink, wanted to try to help folks understand it a little better. So here is a picture that is the thing I don't see is the MP4 link here. And so that I've got to fix. MP4 link to link how it works. Okay. Save image as, what is its name? I'm actually going to real quick see if I can bring that one up from a local copy.
We see you like quick access.
Yeah, I kind of live off of quick access. Mu hasn't been there for a while though. Okay, so that was unfortunately the GIF. All right, well, I'll talk through the GIF then. So it comes around to while true, then it briefly hits pin 14.write digital of 1. And when that happens, you'll see that immediately at that instant, the light in the picture comes on. As it passes through write digital 1, we also get internally a connection to 3.3 volts. That's shown on the schematic. See how the schematic jumps between 3.3 for digital write 1 and 0 volts for digital write 0. So that's the schematic version. Then we have what the microbit is doing for you inside its silicon version. And then we have just basically the relationship of what line of code you're on and what's occurring visibly on the circuit. So that's my attempt at visiting each little step. And there will be a larger size MP4 of this here that you can stop at each little step so that you can see, oh, gee, between while true and write digital 1 is where the light came on, the switch switched and the schematic changed. So I wanted to bring that to your attention because it wasn't really part of the homework, how it works. Also, since we're trying to, help the workforce and electronics, we're introducing some terminology: period, frequency, and duty cycle. Each of those has equations. Each of those has examples of how to solve for one or the other, depending on, which one you're looking at. And I'm going to just sort of brush by this, but we'll actually talk a little bit more about it during the cyberscope segment of this. But there is a little bit of hands-on, how do you make the lights stay on for 80% of the time versus 20% of the time? So they get to try that in the script. And they also get to make it blink faster and slower repeatedly because it's always great to put fun stuff in examples. Next up, setting brightness. Let's see here. Okay, so setting brightness is something you haven't had a chance to do. So let's let's have you try that. Okay, what is the name of this? Oh, so I guess I'll start by pasting the script for this one in. Set brightness with a script and tests. So actually, I should just paste the link in first. Chat. Okay, so here is the link to the page we're on. And then going back, here is the script. Okay, so I'd like you all to try that in your Microbit and verify that that it visits 4 different brightnesses. 1/16 of full brightness, 1/4 of full brightness, 1/2 of full brightness, and 1023, 10/24 of full brightness. And you can just, in this case, copy the script from your chat and then paste it into the Microbit editor.
Andy, is it a true statement that not all pins can handle write analog?
Okay.
Or can you fudge a digital pin because it's not truly?
You totally can, because it's actually a servo signal.
Oh, okay.
It's a 50 times a second or 50 hertz, as was introduced in the measurements section that I glossed over. 50 times a second signal, and depending on how long it keeps the light on during that 50th of a second, you see a different brightness. Because of that, any old digital pin can do it.
Okay, so it acts almost like a PWM.
It does. In fact, we use it to control a servo, hopefully by the end of the day.
Got it. Familiar with that with Arduinos and Raspberry Pis.
Yes, I am. Good. Well, there's going to be familiarity here for the students as well. So, so how did that work? Do you need a link to python.microbit.org? I'll go ahead and throw that in the chat. Okay, so there's python.microbit.org. Above it is the script. You can just copy and paste the script from the chat, and then, or copy the script from the chat and then paste it into python.microbit.org. And we should all already have our light circuits going. And so the only question now is, did anybody plug their LED in backwards and is unable to see it? And although it's sending to pin 14, which according to the circuit I had you guys build is going to be the yellow LED.
Also notice you've got 1023, which in whole numbers 0 to 1023 is 2 to the 10th, but is there a 1024 or is it 0 to 1023?
Basically, if you want 1024, the way to get it is to
write it.
Is to say digital write or pin
14 write digital 1.
There you go.
Okay.
That's the 1024.
Got it. Yeah.
Excellent questions. Keep them coming. Okay, so how are we doing with the chats? Have folks got that light blinking, or have folks got that light coming in at different brightnesses now?
Just like my students.
And I think I might be at the 128 level, given how long it took me to get that.
That's sure to get you a reprimand.
Yeah, that's true. We don't want to end up like that PTA.
And I didn't say they didn't all come in at 1023. And if you're feeling 128, not 1023, that's
Oh,
on you,
that's-
not on me.
Yeah.
I found out 2 years ago, I can't use the expression white on rice anymore. So
Yeah.
go figure.
Yeah, let's see. So after we do the brightnesses, again, since this is a slightly deeper dive, we explain how there's an analog world, which has a continuous range of values, for example, between 514 and 515. But that in digital to analog conversion, you are, going from discrete values that are hopefully spaced closely enough together to make something like brightness look like it's continuous. We talk about counting in binary and how 1023 is 2 to the 10th minus 1, and that there are 10 binary digits, so you can count up to 1023, and that's used in D to A conversion. And these are all very common things in the electronics world, but are not always well understood. Here's a fun one. And so now we're going to try an experiment where we have you grab a script that I send you a link to. So the script name is going to be LED brightness loop up down. So LED brightness loop up down. I'm going to copy this link and paste it in your chat. Control V, hey, Control V, there we go. All right, now what should happen, I'm going to click the link that I see coming from me. Watch my screen, everyone. What should happen, nothing's happening. There we go. Okay, what should happen is you should get a black screen like this with no preview available, but there's a download button. So I want you all to download it, and it should appear as a hex file on your little Chrome bottom ribbon where the downloads are. Then you can go to the Python editor and load the hex file that you just downloaded in and try it out. Let me know if you want me to repeat that.
Why on line 6 did you choose to not set your, I'll call it your step, like 0,1? Is it just understood that at 1023 is going to increase by 1?
Well, I'm going to have to check and see what the author said about that.
I'm going to rewrite it and see. I'm curious.
I think by default in Python, when you do for X in range, unless you add that third parameter, it defaults to 1 for incrementing.
It does, and I put that in this
Yeah,
page. I'm just looking for it because it is. I did specifically explain that.
when I added that in, when I added in the start and the increment, it wasn't happy. So
well, you want to do start and increment.
yep, I did.
See set brightness, how it works. Where is that? Maybe it's in the did you know? Yes.
It's
there we go.
different than
Look at this.
for-
Look.
Yeah.
Okay, so I added this in to bring that up. And the idea is, I want to create questions and then answer them. So I was glad you asked that one. And so when I said, let me see what the author said, I wanted to try to emphasize that hopefully most questions are addressed in this way where, the question comes up and we can see how it works. We can see how it works either from documentation or from writing a little test.
Yeah.
So that's right there.
That's
Then
good.
we have fade in, fade out. Folks, can we just assume that, let's see. Is that the one that we opened? Yeah, we did fade in, fade out. How'd that work? Did everybody get their light to go bright and dim again?
Yeah.
Good, good. Just make sure to shout out if you need some help. But the most common mistake that occurs is that students don't catch the part about making sure to put that longer pin on the positive side of the circuit. They put this in backwards. And so that is a thing that, oh yeah. And then again, there's a reminder to remove the 20 ohm resistor for those who did the current measurements. We don't want that 20 ohm resistor sitting here forever. All right, so so what comes next? Okay, adding a light. Let's gloss over that in the interest of visiting. Well, what the heck? Let's try this. I'll just paste it to you. Okay, so since we're doing the build it all and then test it all later, hopefully what you see is now the green and the yellow light turning on apparently in tandem and then turning off apparently in tandem. And then a fun thing to do after studying how it works is instead of turning them both on, which would be 1, 1, or which was 1, 1, you can change it to turning one on with 1 and turning the other off with 0, and then reversing the arguments so that pin 13, which had a 1, now gets a 0. And pin 14, which had a 0, now gets a 1. And then when you
Railroad crossing lights.
yeah, when you reload, oh, that's a good analogy. Railroad crossing lights. I'm going to write that down because actually I want to add that since it's a real world example. Thank you. That's excellent. Okay, let's see. Intro to lists. So this is part of salting in computer science concepts into the mix because electronics has really become increasingly dependent on computing. And so we want to, as much as possible, introduce computing concepts. And in Python, this is called a list. In other languages, similar things called arrays exist and or structures, depending on what properties of a list you're thinking about. But regardless, it's a common thing. If you need a custom list like green, yellow, red, well, how do you get that? How do you say, well, I want to shout out green first and then shout out yellow next and then shout out red after that? Well, here is the program that does that. And then they get to try it out. And then they get to see step by step how a list has elements. In this case, its name is C list. So we had C list of 0, C list of 1, C list of 2. Then going through color equals C list of 0. That's this one. So it becomes that, which gets copied over to color. Then we print it. There it is in the print statement. And then we add one. Well, index started as 0, so it shows that the +1 index becomes 1. Then we check if 1 is less than the length of C list, which is 3. It wasn't, so we go through and repeat it. And I want to emphasize that this is why we put one of the reasons we put the MP4 in there is so that you can close. I need to close some tabs and then try again here. Okay, so now you can pause it. And for example, we can say, hey, look, if you want to get green out of CList, you use CList of 0. If you want to get yellow out of it, use CList of 1. These are the indexes of these elements. This is the name. And then go through and see that index, which was set to 0 right here, is still 0 right there. Well, there's CList of 0. See, CList of 0, that's a 0. That means green. So that's what CList of index replaces when index is 0. So now it has green, which gets copied to the color green. And you can actually really dial in and talk with your students, have a group discussion about this, make sure that everybody's really understanding how it works. How's that look, folks? Does that seem like a teaching tool you can use?
Yes.
Okay, good. I am open to discussion. I felt like this was pretty much done. Like, the way we're showing the values is fairly unobtrusive. I mean, it's true. It does come over some of the other text, but really, since this is the line of interest at this point, I think we're okay. I experimented with having it right over the name, but it just didn't seem, it seemed like it obscured it.
One question. Maybe it's just because we've got short classes and such, but rather oftentimes I'll introduce variables first, where they'll be able to see that I can assign a variable that I want my green. So my green is now going to have this function to it. So if I want green on, green off, kind of going that way, and I can see that I can define green, define yellow, define red, as opposed to remembering pin 14, pin 13, pin 12, but then getting through and then bringing them into a list in an array environment. I was just curious if it's just a time constraint or.
Well, all right, so.
In middle school, variables is one of those magical things that I have a blast teaching, and it's really great to watch their light bulbs turn on, because then I'm able to go and take that and make more sense out of my shopping list, if you will, in this array.
Yeah, so a lot of this gets hit in that prerequisite. So I had you guys visit the prerequisites, but only in a cursory way.
Got it.
And so that's one place where you'll see a lot more use of variables than just the addition and subtraction that you did in the prep homework. And then also, I want to say that we got that. Well, so this is the sequencing right here with the actual lights. Let's talk about that after the class, though. I kind of like that idea of basically saying green equals pin 1, yellow, or pardon me, pin 13.
Yeah.
I hadn't thought about that. That's a fantastic idea. I want to use it if you're okay with that.
Yeah.
Also, Andy, bring it up constants. For example, instead of feeding a 1 and 0, you can have, on and off.
Yeah, okay.
Or high and low. Or...
High and low, whatever, the information hiding.
Yeah, we can do that afterwards. Some of us can stick around so we don't eat up your time here.
Okay, no, that sounds good. I took those as notes. I'm already thinking about in the background where to exactly put those things. Okay. Now, this is pretty important. I want you all to try this. I'm going to give you this link And but before I give you the link, I just want to show you LED blink with voltmeter. Okay, so we're going to right click, select Save As, and then let it download. After it downloads, we'll go to our Python editor, hit load save, and drag the file we just downloaded into the load box. Flash it. Disconnect. And then go to Cyberscope. And there's one other thing I need to show you, and that is that you're going to position your probes in the same row as P13 and on the and a socket to the right, to the left of the blue stripe, immediately to the left. So you'll need to put your probe in P13, which is row 17, either B, C, or D. And then one of the minus columns over here for your black probe. I'm going to get that real quick. Okay. So that's the circuit part. Then we just loaded the code. So it was connect, flash, then disconnect. Then over in your Cyberscope, hit connect, choose your port. And what we want to see is around 2.7 volts when the light is on and around 0 volts when the light is off.
Yep.
And this takes us back to the theory versus practice. The I/O pin has a certain amount of built-in resistance. And so when you pull a certain amount of current through it, you're going to see a voltage drop inside the microbit before getting to the LED circuit. So that's why we don't see 3.3 volts. It doesn't have a strong driver, because the microcontroller is actually designed to be a fast communicator, and fast communicators and strong drivers in terms of I/O pins are somewhat mutually exclusive. Things that can drive a lot of current tend to respond more slowly. And that is explained in the text. So I am hoping that everybody sees this, because it really helps. I think it's an excellent exercise for students to be able to probe that light and see, hey, look, we got voltage applied when the light's on. Okay, then the voltage goes to 0 when the light's off. It's another avenue of reinforcing how it works. And did I forget to give you a link? Let me make sure that.
I got it in there for you.
Oh, thank you. Okay.
With a microbit, is there a way of stepping up voltage to get 5 volts? It doesn't
Well,
really-
okay, so there is a way. Now I included some transistors in your kit because one of the things I want to do later with this is connect a transistor to P13 and observe that the transistor voltage is closer to 3.3 volts than the pin supplied voltage was, along with several other things with transistors. I have not drafted that part yet.
Okay.
But that is coming. I'll also be talking about what the plans are and when roughly to expect stuff on Friday. Okay. How's everybody doing with that? Have you all got your alternating 2.7-ish and 0 volt displaying in the Cyberscope voltmeter?
Yeah.
Okay, I'm going to keep moving. If anybody's feeling stuck, give us a shout out. Otherwise, I'll show you the oscilloscope version of this. And there was a question. I might actually need a reminder of what that question was. I think, oh, it was duty cycle. It was Alan's question about duty cycle and frequency and explaining it to the students. So let's see, here is the next page. Our circuit doesn't have to change. Paste, there we go. Okay, so there's the next page to go to. And same routine, I should do this properly. We're going to disconnect from Cyberscope since we're done. And then right click LED blink with plot.hex. Select save link as, save it. Then go to the Python editor, that's python.microbit.org, and drag it. I use the Windows shortcut, pardon me, load save. That works for all systems.
Is there a reason you've got to sleep for 1 millisecond? Is it just that there's roughly like a 1 millisecond offset with commands?
Man, you're fast. Yeah, basically, this is a patch.
Yeah.
Something wasn't working so great plot-wise when I didn't wait before checking the measurement, and I don't know what. Normally, I prefer to oversample, but there's drawbacks to that when you have a web-based oscilloscope. If you try to plot too many points, it can choke.
Yeah.
And so, so this was my best, my least bad alternative. So click connect, flash, and then disconnect, and then go back over to Cyberscope and click connect. And since it's in auto, as soon as you click connect here, it should switch over to plotting. So I want to wait for folks to catch up to me here. I want as many people as possible watching the plot marching across the screen on their Cyberscopes and oscilloscope view. So can I get a shout out when you're all ready?
Yes, you can.
Okay. Let's see here. I might be able to multitask well enough to see the chats.
Will you also, at this, explain, I mean, I understand the difference of trigger of rise and fall, but when I go and lock it in, I still have the offset, even with 1 millisecond and 499. And I was just curious if it's just that interface between virtual oscilloscope versus electronic.
Okay, so I will, while we're letting folks get to this view, I'm going to try to address Alan's question. The first thing I need to do is understand it a little bit better.
So I set my time divide to 500 milliseconds just so I had a bigger view. 250 is fine.
Okay.
If you notice that it's shifting. So if you set your trigger to rise, and I lock that to 500, that's cool. Notice that on my second rise, I'm really still offset. I'm at 15.
Ah, that's your question.
Yeah.
Gotcha. Yeah, and so that is explained in the text as well. And it's actually left to the student. Basically, the problem here is that, you know, the same device well, okay, this would be a problem for many devices. If you don't have a built-in way of making sure that your time is deterministic, you're going to have a certain amount of execution time. So when I say high, or when I say write digital 1 and then sleep 1,000, well, there was execution time involved in interpreting each of those statements.
Yeah, you can see it's like 8 millionths.
Yeah, now there is, of course, that extra 1 millisecond I added in. I don't remember if I, see here. Oh no, I did at least say 499.
Yeah,
But you see, the thing is 499 isn't enough. And so it's up to the students if they want to see it looking nice to hunt and peck and get something so that it lines up nicely. But this is a good way, in my opinion, of also showing, hey, there's reality here. There's processing time. It takes a while to fetch those commands, interpret them, and execute them. And that while is visible here. And there's also the amount of time it takes to communicate communicate that to the between the microbit and the cyberscope, because it has to be sent over as serial data.
It's
Can I ask a
interesting. I
question?
got rid of the sleep ones and I get a very different,
Yeah, it looks pretty ugly, doesn't it?
yeah, it's,
I heard another question.
Well, my graph looks like a line plot. It doesn't, do I need to select something so it looks different?
Well, let's see. Basically, if when you
your vertical divisions.
It's the same as the screen. I'll just play around.
Well, we can also have you, we can also share your screen. I can unshare mine.
No, if I'm the only one it's happening to, I don't want to interrupt everybody.
Okay, what we can do also is I'd like to make sure that this works for you. Can you email me or who am I speaking with? I'll email you to set up a
This is
Zoom.
Amy Kaufman.
She's not
Okay.
the only one. Mine did the same thing.
Okay, and who are you?
Felicia,
Felicia or Alicia?
with an F.
Okay, Felicia.
So what I realized was if you mess with the numbers on curve smoothing, that's when the lines, it gives you a straight line.
Oh,
Oh, okay, yeah, because curve smoothing will give you pretty, it allows you to plot backwards in time.
but I don't think that's what they're saying though, if they're saying a flat line.
No,
Yeah,
flat
It's
line.
not flat.
It might be horizontal, means like on a diagonal, right?
Mhm.
Okay, so it's
It's like a
kind of
line
going
plot.
upward like that.
It's like
Oh,
it's plotting individual points and then connecting those points instead of having it be on a
Right.
continuous graph.
Yes, so you can actually play around with all these numbers and you'll find those lines.
Okay.
if
What's
you
your
see
what's
my-
your time per division set to?
Yeah, if you
Right
look
now,
at my-
1,000, but it,
Try 250.
So if you look at my screen, I'm Alan. If
Hi.
yours is doing something like this,
it's not, but it's kind of like that, just on
so
a bigger
I
scale.
changed, yeah, I changed these. So if you go back up to like 500 milliseconds, your time division,
Mhm.
or down, you know, even to 1,000, that should slow it down. You should get your highs. If you're getting down in that, 1 millisecond range, your divisions are so fast that it may not be giving you your rise and fall.
Mhm. I'll play around with it, but thank you.
Okay. And can I get anybody else to call out if it's not working for them? Because I would like to set up either a post Zoom meeting or just a Zoom meeting at a different time so I can help you get that working. Let's see here. Share screen. Okay. Now, for those of you who have it at say 250, but have not set the trigger yet, what you're going to have is a high-low signal that kind of seems like it marches across the screen. I think I'll get a better example at 500. So it's marching its way across the screen, and then the whole waveform is moving to the left. And so one of the things I want to show you is how to set it to 250 as your time per division, and then set the trigger, which is down below, to rise. What that's going to do is it's going to make some crosshairs appear. And then after around twice the amount of time is along the bottom. So this is 2,500 milliseconds or 2.5 seconds. So within 5 seconds, you want to see the plot. You want to see the plot's rising edge snap to those crosshairs. And you can actually move the crosshair over, and then the whole plot will horizontally move over within about 5 seconds.
And that's because you're waiting for the plot to finish its current one and then update the new one.
Correct. Thank you. And that is what's happening. Yes. And there is a comment to that effect in the text. All right. This will come in very handy later. So the next thing I'd like you to do is, and I need to make sure that I'm doing things right here. Let's hit disconnect here after we've observed the trigger. We'll be doing more with that later in a more real way. But so right now, let's disconnect the cyroscope, and I'm going to share another code example with you. Let's see, let's just jump forward to push buttons. And there's a lot of push button stuff here, but in the remaining 8 minutes, what I want to do is just have you test both push buttons to make sure your circuit is okay. I'll do a very quick thing about some of the stuff that we introduce. Now, this is in a Google document because this has not been flowed to the web yet. Okay. So I just want to note a couple of things here. The first is that when you or your students plug in a push button into the breadboard, they want to make sure that the pins are sticking out the side of the body. And then they're supposed to go in so that the body of the push button bridges the valley in the middle of the breadboard. And so there is one of the steps. Now you have both push buttons built, but this is the first push button that they're testing out. And they're going to try it out, and they're going to see zeros and ones, depending on whether they've pressed or released the push button. Then here is another how it works type of video where it essentially shows how the voltage in the circuit that is measured by P6 changes depending on whether or not you've pressed that circuit. It shows it in schematic form, it shows it on the breadboard, and it also shows the 1 and 0 that the, and we talk about input pin registers in the text as well. And then it shows your more, well, gee, when the button is pressed, pin 6.read digital returns a 1. And then when it's released, it returns a 0. And so that's a good thing. And then what I did was I actually set up some questions so that the students could, and by the way, about the, yeah, there was an earlier animation that was fairly in-depth too. And whenever the animation has a lot going on in it, what I do is I have some questions so that the students slow down and can be prompted to think about things in a little bit more detail and come to a better understanding of it than just glancing at it and moving on. All right, so let's see here. The crossed out ones were put in the assessment material as far as these end of chapter things. And let's see here. Okay, so here we're measuring, oh, now we start with measuring the light. And this is the inside the push button. So this is another thing I wanted to talk about. The reason we want those pins sticking out the side of the push button's body is, I hope everybody can see this fairly clearly. With a push button, when you're not pressing it, it's hovering above two wires that are passing through the body. And it just so happens that the wire sticking out the side is bent down, so it looks like a pin. See how that works? That this pin 3 here comes around and becomes pin 2, that they're always connected. And then that's the same for pin 1 and 4. And so earlier we did some probing and continuity tests to better understand breadboard sockets. And we again do probing and continuity tests here. But for fun, before we end the session, or before I call out the homework and then end the session, what I'd like to try is, did I lose that? Shucks. Okay, I need to get back to Google Drive. Okay, there we are. And
It's because you've got a link. Just do drive.google.com, because that's the link for that other file you had to stick. There you go.
I don't know where I just ended up. Okay. On my way back to the workshop links. And I'm going to share another hex file with you. So we're going to have you do the first Servo activity on your own as homework. Because that's next up. We're going to do a real quick push button thing right now, just to test your push buttons and make sure they're working. Where the heck is the push button controlled stuff? Okay. I apologize for the delay here.
The hex file, or do you want to just paste the text in?
I'm looking for the hex file, I think. I'm looking for the sequencing. So there's the measure push button. I believe that sequencing comes before that. And it's probably with the second push button. And so if I can find the script name, which should be a ways down. So here's where we test 2 push buttons. And then we blink 2 lights based on 2 push buttons. And then here's the fun sequencing stuff. Buttons make LEDs rotate. So then back to the Google Drive. Buttons make LEDs rotate. Okay. Looks like I didn't get that one into the, oh, I can paste this in because this is still in draft form. So we have what's going to be hidden in the teacher's guide. By the way, I always set it up so that there's something that runs that the students can try first. And then there's screen captures of code to prompt the students to go through and make some changes to the code and actually get their hands on the keyboard. But let's see if we can get this whole thing into the chat. paste. Okay. Now, did that give me everything? I think it did. Yeah. So if you grab this and paste it into the Python editor, we kind of took a big skip forward. I skipped over some of the testing, some of the looking at 2 push buttons with this and what they're displaying for their states and stuff like that. But hoping you guys are all okay with that. If it were a longer course, we could go a little bit slower through there.
Oh, that's cool.
You like that?
Yeah.
This also, just so you know, it puts together some of the stuff we were working on with lists. So it gives it a more meaningful application. And then make sure that you can press and hold one push button and the green, yellow, red sequence goes. And if you hold the other push button, the red, yellow, green sequence goes. You want to press and hold the push button after loading this code. And folks, if you could hang with me as a large group for just a little bit longer, I want to give you a quick preview of the next homework. Which I'm going to have to change slightly.
Mine did not work.
Oh,
Okay. Now hang afterwards with us, and or we can set up a meeting time. So what we're going to do is the first servo. Okay, so we're going to do the initial servo activities. And so servo position control. So you'll basically be opening up a Google Doc, and I'll send you the link for this. And we'll have you do the first 2 activities in this Google Doc. And so the first activity, so first of all, don't take your board apart. Keep everything that you've built because you'll need it, or at least the push buttons. And so then we're going to get the battery pack, battery holder, and put the AA or AAA batteries in it. And we're going to connect that to the Microbit edge connector, not back here in the Microbit, but to the edge connector, just as shown in the picture. And then the leftmost bus strip is going to have the battery voltage. The rest of it will have the regulated 3 volts from the Microbit, but this left strip will have your battery voltage. And because of that, and so we'll measure it with a voltmeter. And then after that, we'll go ahead and take out the servo. You'll be grabbing a servo, and then this thing is a little armature that's in the bag with the servo. There are several different shapes. These are called horns, and you're going to get this horn and the servo. Then what you want to do is push the horn onto the output shaft here, and then rotate it very gently until you feel it run into an internal stopper. This has about 200 degrees of motion. And so you want it pointing at about -10 degrees. So it may stop anywhere else in the circle. You're just going to turn it clockwise until it stops. Then pull the horn off and then push it back on so it's in this orientation.
all right.
After you do that, it's going to guide you through building a servo port, which is the power, ground, and signal to control the servo. And then you'll be plugging in the battery, loading a script, and you want that script to make the servo turn to 0 degrees, which is roughly, oh, here, we'll go to the animation for this. Okay, so you want the servo to turn to 0 degrees, 45 degrees, 90 and 180 with that test script. So that's what we'll have you go through for homework. It's going to be kind of fun.
How many servos could this microbit run?
I'm not sure. I have not tried. I know that you can run 2 for a little 2-wheeled microbit robot. Now, one last thing about the homework. I also want you, most of you apparently already have accounts on learn.parallax.com. So, and I'll be emailing you all this too. But basically, if you already have a learn.parallax.com account, go and make sure that logging in works. If you have not previously signed up for learn.parallax.com, you will get an email that looks like this one. And so you'll want to follow the link, and it'll, I think, guide you through setting up your password, and you'll already have a username that is part of your email. And after that, make sure that you can go to learn.parallax.com/user/login and log in. And then we'll show you some curriculum stuff where some of the assessment materials with solutions live that we want logged in teachers to be able to access, but nobody else, especially not the students. And on Friday, we will be doing some Q&A. We will pick back up on the simulator, circuit simulator, trying to decide what's going to be best to amend to these lessons. And we'll talk lots about curriculum, where to find it, what different things you might be able to use, and stuff like that. And if time permits, I've got some fun projects to show you. And that's it. Is anybody left?
I'm here.
Okay, good.
I don't know. I guess no one told me it was time to go home yet.
Oh, yeah, I think, let's see. Whoa, is it? Yeah, it's 1 to 2:30, isn't it? For the schedule?
Oh, it's
Yes.
5:30 here.
Pardon me, 1 to 2:30 Pacific.
Pacific, yeah.
Real time zone. EMT -8.
The only time zone that matters. All right. So let's see. I have a list of people. Is there anybody else who would like to? I mean, first of all, we can try to get past any technical hurdles for anybody who wants to stay after. If you have questions, or we can have you share your screen and maybe glean what's happening. Otherwise, like I said, if you just give me your name, I can email you for a time to just do a short Zoom meeting to make sure that your system's working well for you.
Yeah, I'd like to stay and figure out why the sequencing with the push button's not working. Everything else did, so I'm trying to go over it right now while you're chatting.
Okay.
Mine turned out to be my fat fingers, which put the wire in the wrong hole. So, I have to get some narrower fingers, obviously, because it gets tight working in there. But
Just play with a pencil.
no, I get my little handy dandy plier piece now, so I can shove it, or scissor clamps.
Yeah, like this beauty right here.
Yeah.
Andy, this is Debbie.
Hello, Debbie.
Hi. I know it's particularly quiet, but I just wanted to know if there's like a list of troubleshooting items that you all have that kids could go through, like check this, check that, because that's what I did when one of my circuits wasn't working, but I was checking through. So is there something is there something like that for every exercise, something to troubleshoot, or?
No, there is not currently.
That's actually the term that I use, though. So Debbie, with my students in middle school is a great place for teaching this because they screw up a lot. First thing I tell them to do is go back and double check the schematic. And I always tell them, look at things like polarity, which is, for an LED, is the anode and cathode plugged in correctly? And always follow their wires. As I was listening to your beautiful accent, noticed that I just had one that was shifted over to the wrong rail. So all my code is fine. Everything was set up right. But I had something that was short circuiting because it was going over into a positive rail when it should have been a negative. Now all mine works beautifully. Typically it's just those.
Now I notice that like if you have errors in your code, when you go to the terminal, you see the exact errors, like indentation and blah blah blah. But I was wondering if you can have a program that sort of in the terminal kind of like, oh, check something, check this, check that. Do you know what I'm saying? Do you understand what I'm saying, Andy?
I do.
I don't know if that's logical, because I'm a software engineer but I'm not really an electrical engineer, so I don't know if it makes sense for this.
Well, no, it completely does. The troubleshooting documentation is fairly common in certain instruments. There's just, the manual comes with it. It has a troubleshooting guide. And I shied away from that mainly because I already felt like I was putting quite a bit of weight on the amount of material that was there. And so having a troubleshooting section for every section seemed like a little bit much, but what I'm thinking is that I could add pages saying troubleshooting. What if you made this mistake? Here's how you might be able to test to find it out. And if instead we salted some troubleshooting tips as we went, because for example, first you start with code. So the troubleshooting is, what if you make a typing mistake? How will you find out about that? Then later, what if you put it into the wrong socket? And then that way, what we can do is hopefully grow their ability to think analytically about what mistakes they might make and how to catch them. How does that sound?
Yeah, that's my idea. That's what I was thinking.
Okay. Oh, good. Okay.
I didn't know if it was logical in this aspect. That's what I.
Oh yeah, it's completely fine in this. And another thing is, maybe I had to skip a lot, but when you go through it, it's very methodical, very step by step. So for example, we build one, I had you guys build all the lights and all the push buttons in one night, but the tutorial, when it steps you through it, it's like, okay, here's the parts for one light. Okay, now we're going to put it together. Then we're going to test it. Did it work? And by one of the engineering development terms is subsystem isolation. And so the idea is, if you have a system like a light and then a motor and some push buttons, you want to get each one working and tested on its own first, and then you integrate them. For example, a push button controlled servo is something that we will do next time, because we've built our lights, we've built our push buttons. We're going to add a servo into there. Each one gets tested individually, and then only after they work individually are we going to start trying to get them to work together in concert. Check the push button, move the servo a certain direction, kind of activities. And so that's another aspect to electronics and the technician and the engineering world, where everything needs to be broken down to its smallest possible component, make sure it works before you move on. And so that's a habit that all of these tutorials are developing. And yes, I'll see what I can do to salt in troubleshooting, what if you're stuck on this, as asides along the way throughout the lessons. How's that sound?
I mean, if you think, yeah, I mean, I was just thinking that because we still, you know, an instructor may be moving a little faster, and sometimes you just kind of want to know where was the error. And I mean, like you said, it is logical. Yeah.
Well, I mean,
Tutorials are pretty good.
I have
Just
an example. Andy, that I think Deborah answers.
like what just happened right now, you know, if we can take the example of where you know, had a bomb site. Oh, I see what you're saying. Okay,
So
let's
if
see.
you-
Can I share
Yeah,
this?
others can just pin my screen. This is from something else that I use. And they've got, you know, there's example, this is in C, it doesn't matter, but then you just got a quick like, okay, it's not working, and forget about what the lesson is particularly, but okay, some don't light, some LEDs fail to light. Okay, maybe it's backwards, right? Or it's out of sequence. Maybe double check that the first one's plugged in correctly. Just a few, it's less about a detailed troubleshooting, but maybe it just goes in and kind of hits that.
I think that's great. I would love to get a copy of that.
But this,
Did you
well,
make
this
it
is-
up?
No, this is for something else.
Whoa.
This is in C programming and electronics that I teach with Arduino. But one of the things that I liked about this is they just had other bits and pieces in it, like you were saying, that with code, if it says error on line 27, it's either 27 or something before it. I can find that. But you're right, like with what I was just doing, and I think Edward was, maybe you were talking, someone was saying fat fingers. You know, sometimes I just stare at this, and when you've got 42 resistors and 36 wires and 12 LEDs and push buttons, it just becomes a lot to go over. So you just have to stop and really go back and say, okay, what was the deal? Mine wasn't sequencing. Okay, well, if it's not sequencing, it's probably a power issue. So that meant that I had mine plugged into the wrong rail. So it was really like, here's just a few quick things to go back over. And that's why I liked this particular document. But Andy, I'm happy to share that.
That's pretty good.
I mean, it's a public domain document for something else, but why don't I just put that in the chat?
Yeah, sure, that's fine. The thing is though, that I can see a way now to incorporate troubleshooting, because it really does need to become a habit. And so it should actually be a little side activity where essentially we can say, okay, well, let's say that on this light, you connected it to the wrong socket. How would you discover it? Okay, let's connect it to the wrong socket. Let's take our voltmeter out and take some measurements, think about what we expect, think about what's really happening, and then set up an idea, a hypothesis of how to fix it, and then test that hypothesis and eventually come across the one or more problems that are in the circuit. And
maybe that would be a great 3 different lessons of whether it's a simple circuit like just an LED lighting or something more complicated. And then, you know, the diagram will be wrong, the wiring will be wrong. The circuitry in terms of your the actual layout can be correct, but then why didn't it work? And then you can also have a solution to that. This needed to move, that resistor needed to change, this voltage was incorrect, etc.
Yep.
And that walks them through just the simple thing of anode cathode flipping all the way to a more complicated circuit. That would be great training in using all of those.
Yeah, I really think we need to formalize it, because troubleshooting is truly challenging.
It's more of an art form, and when I trained adults on that years ago, I come from industry. What we would do after a section is we had a list of bugs, which we would induce into the machinery. And then the student, how did he demonstrate mastery? He would troubleshoot the bugs. That's a little bit different than what we're doing here, but I can see where that might be a possibility. I mean, I've not done that with the students. Normally they can introduce enough bugs on their own without me having to change it. But Yeah, that's a hard thing to teach, and some people diagnosing hardware never really pick it up. It's an art form and it's a mindset. I used to think it could be taught. 30 years in the industry told me that no, it can't necessarily be taught.
Well, not everybody's going to pick it up, but I still think if our documentation does due diligence, that what we can do is show examples of debugging your code, of debugging certain circuit mistakes. And that way, if they're salted in along the way, also, Ed, you mentioned that it's an art form. I completely agree. And so having repeated experiences of
you'll get some competency. I agree with that. Yeah.
Repeated experiences of different flavors. One time it's going to be, oh gee, the code isn't indented on line 3. And then, the next time it's going to be, oh, the circuit's in the wrong spot, or the clip wasn't properly attached. And if we can have just basically activities where we say, okay, this is a troubleshooting activity. You got it working. Let's break it. And then think about how to actually find that if we didn't know it was there.
But writing the code in small pieces, I mean, that's software troubleshooting and hardware troubleshooting, as I've been on both sides, are very different animals. I mean, at least from my viewpoint, okay, software engineering is smaller modules, testing the modules, and then putting them together into the larger program. Which is, I think, different than hardware. I mean, you talked to Andy, you mentioned before about, students going into the workplace. I mean, I think the first experience the students are going to have in the workplace is you have a piece of machinery that was functional at one time.
Yeah.
They're not developing it. They're trying to find out, okay, the assumption is this worked. Now it doesn't work anymore. That's different than when they're building stuff here, because there is at time 0, they're putting that together. It's not that, oh, here's a circuit board. Okay, tell me what, did the transistor go bad, or are we having, something else go wrong there? I don't know.
Well, so one of the nice things about what we have here is that you get both worlds. When developing products, I have many times pulled my hair out for 20 minutes over the code, and then realized, wait a minute, what if I made a mistake in the circuit? I mean, the result is not what I want. And, my first instinct was to look at the code, but gee, I'm stuck with this code. So what about the circuit? And, lo and behold, there was the problem. And so, there's, especially with inventing and with robots, hopefully there's projects that like students end up in senior project where they have to troubleshoot their project too. And if we can just give them some experiences along the way here, just to get them ready, hopefully a certain percentage of them will remember that experience and say, oh, wait a minute, I don't always want to focus on the code. Maybe there's a problem with the circuit, or vice versa. And so that's, again, part of the art form and part of the idea behind having troubleshooting wisdom sort of inserted at spots along the way through the lessons.
Andy, going back to the area where you did the frequency, the duty cycle, you show the equation one way, but then when they're solving it, it's not lined up the same way. All right.
Okay, just a minute. Let me get there.
Okay, just go back there for a minute. I didn't want to hold up the class at the time, but
yeah.
I like all your pairs of pliers, by the way. let me see if I find it on mine, it won't help because you can't see my screen.
Okay, it was at the, it was
It's
in
where
the,
you introduced the frequency, duty cycle.
oh, that's
Measurement
right.
units,
Yeah,
isn't it?
No, it was actually, measurement units is kind of a precursor
yeah, it's
to,
not measurement. Oh, let me find it again. Oh.
oh, it was right in connect and blink a light.
Yeah, connect and blink a light. That's where you first start to talk about it.
Yeah, so
Okay.
measure
This is-
blinking. Well, let's see here. It was
Oh,
here we go. Here we go. How it works.
No, this is.
There it is, on off signal. So I'll go ahead and paste this.
Okay, move up.
Yeah, bear with me. I just want to paste it to the group
Okay.
so everybody has the thing we're talking about. Paste. There we go. Okay, so
You see, for example, okay, going down here, okay, so you're showing F is 1/T, right?
yeah,
But then when you're showing the example that they're working out, it's changing to where you're going in line on a single line, okay? And from teaching mathematics now, putting on my other hat, we're showing it the way you show it, the blue, where you have F is 1/T. Okay, when it get, I would have the examples look like, I'm pointing at the screen. You can't see what I'm pointing at.
no, I understand what you're saying. You're basically saying that I did it more the way you'd write it in this image, and then this is in text.
Right.
And that could be a point of
Some of the
confusion.
some students, ones who are weaker in math, get confused at looking at it that way. Especially when you get down on the bottom, further on down the page. And, now you have, where is it? Yeah,
That
right
duty
here.
cycle.
Okay. You see where now you're calculating the duty cycle, especially when I look at, either one of those examples. I don't know if it's possible because I don't know what editor you're using. I would
Well,
just,
it's possible. Basically, these are images of PowerPoint is where I just took some screen captures of doing it in PowerPoint. There are lots of equation editors, but they're generally
most of them are a pain in the,
took us. But aside from that, it's really hard to make them look approachable. The formatting, adjusting it to get it to look more like this is really tough. So what you're saying is basically we need to quit doing inline text. We just need to stick with the images.
I don't know. It's the way we're teaching that, it's the way we're teaching now. And I guess, I don't know if this is other parts of the country. Obviously here we're from one, East Coast to West Coast.
Math was never really meant to be written anyways.
I understand that, but I look at, I look at the students, I've been teaching math now for the last 4 years. Because I got forced into it, and this is questions they come up with and questions I get repeatedly. Again, not, the faster students get it, but you look at the math skills of many students today.
Well, okay, so the question is, do we want to do it like this, or do you remember where I actually wrote out the solution?
I have another suggestion.
Yeah.
Okay.
So Edward, see if this sounds good. I like, Andy, that you wrote it using the screenshot, right? It's a good visual because we talk about that, X over Y. But in the grand scheme of things, 90% of what we're using is really using a / and writing it out more in a textual based environment. Perhaps as part of that graphic. So let's look at the one that's on the screen for your percent duty cycle equals.
Yeah.
Maybe if next to that, it's written that this equals so that you can, maybe there's some, or I don't know.
It's true.
I don't know that you guys need to teach math. So I understand, but I understand what Edward's saying too, that when you take it from the, over and under to side by side, some people get lost.
Right. When you get students who've never even covered PEMDAS or whatever, and I'll be honest with you. I mean, I understand what you're saying. I don't have to do it, but I do have to do it. Okay. When you give out a test and out of 100 points, you have half the class scoring below 30.
Oh no, I didn't mean we don't have to, Edward. I was saying that.
Yeah, no,
Parallax.
I don't know. It's the way we show fractions and the way we do algebra, okay, and or the way we're trying to standardize on the way it looks.
4/3 of Americans have problems with fractions, anyways.
I know, but that's what they need to know. That's what they need. Well, yeah. Take away the digital clocks and give them analog timepieces, and we'll solve the problem.
There we go.
It's like I refuse to tell the student what time it is, other than to say it's a quarter after, quarter to, or half past. What time is it? Well, I don't know. You better figure that out. But the fractions are a strain. But that's in order to pass and to get out to earn. I teach adults as well.
Well,
I don't want to get off topic here. I mean, it's just if it's possible, I thought it might be better.
I noted it, so it's in my notes, and one of the main things here is that we get feedback from you teachers to find out what you need, because if we're not making something that's useful to you, you won't buy it, and then
it's useful.
Wasn't worth the effort. So
no.
So we got to do it right.
It's not that it's not useful. It's just that I come from both halves of the house now, the homeschool and the public school, and I inherit kids who are just, the math skills are just, what were you doing for the last 4 years?
Yeah, well, I was a little bit concerned about what you pointed out, so it was already in the back of my mind, and so it seems kind of like we've got some consensus of the folks still here. Thumbs up or thumbs down? Would you rather? Yeah, you want to see that everything in the similar format?
I think if you saw things side by side, it would cover all angles, but from my experience, what I've seen students do, like some students get caught up flying it and seeing more students would want to see the graphic image of, X over whatever, rather than slash whatever. But we do have to have that understanding. So if they were side by side, I think that would be the best approach, kind of cover all your bases.
Well, on a text edit, I mean, the one reason why we, did the slash is going back to the early editors on the screen, right? Before we had a visual thing, you have to show it that way.
Well, and another thing is when you're solving for it in code, that's a mental jump that needs to happen.
Yeah, because you don't get the horizontal bar anymore.
No. And
maybe it should be left the way it is. I don't know. It's just something that popped up to me mainly because of the time I spent teaching fractions and teaching algebra. I mean, I have maybe a different approach to teaching. I teach them that there's no difference between, fractions, decimals. It's all different representations of the same number, but they depend a lot on the visuals. I mean, I have students who come from all backgrounds and have all different abilities.
Yeah.
That's the other thing. I don't get to pick my students.
So I think if at several points, because thinking about this a little bit more, they are going to have to make the jump from this to text if they're going to codify a solution.
You're right.
And so,
But it's like
with that in mind,
Randy, what you have there, I think, I mean, and I understand, Edward, exactly what you're saying. But I think what you've got there, Andy, is you've got the graphic representation of sort of mentally what we're talking about, where, you know, it's T high over T times. And if, as a teacher, I'm showing this up on my interactive smartboard, I would go over and maybe draw a line, and I would show that here's where T high is sitting up top. Here's where it is in line. And it does require, like what Edward was saying, is frequently with my first year engineering students, that I'm teaching a lot of mathematics because it's an open class that anyone can take as an elective. So there's nothing that even says you need to understand basic algebra or basic PEMDAS or simple math. With my advanced students, there's already an understanding we're getting into higher mathematics. But you know, it's math, and like you said, no matter what, when you're doing this in Python and C and Java and whatever
it's
you
gonna
do,
look like this. You're right.
Yeah.
Yeah, yeah, and I'll be honest with you, I hadn't considered that. So now that I'm hearing what you're saying, yeah, okay, this makes sense that you're gonna have to learn, and you know, it's also a teaching opportunity to explain, you know, how stuff got moved around here. So yeah, this may be the way it should stay.
well, I think that there needs to be a transition where at some point, at least, we say, hey, we just gave you an equation. Well, guess what? You know, that equation can also look like this, or in code, it looks like that.
Yeah.
And then that way we kind of cover the bases.
So maybe there's a worksheet, Andy, and or Edward. Maybe there's a worksheet like some of those other questions that say, please rewrite, you know, this graphic as code. And it could be really simple. You know, R equals V over I or whatever, you know, or I over E. It's just something so that we're just taking them from, call it visual to textual, and just a few worksheet type problems that let them
Well, we are doing it, Alan, because you know what? In the next page is when they start writing the code now for this and doing the calculation, right? We didn't do, I mean, I have to admit everything. I'm starting to see this now. We didn't do every exercise.
Yeah.
So when they do go through this and they're calculating it on that one example, which is further down somewhere, they are going to see that it's in line.
Yeah.
So, yeah. All right.
Look, engineering and programming, software, hardware, requires some mathematics skills. They don't need to be, you know, for what we're doing, they don't have to be brilliant rocket scientists here, but there are some basic mathematics skills that may need to be front loaded on our part as a teacher to make certain that as we jump to, you know, the first introduction of something like this, our students will be able to take that mental transition and visual transition between the two.
Yeah.
So I think that the best opportunity for this is probably right here, because we start with
And
this.
there's a manipulation there. So that's good, Andy. You know, where we saw here, you know, what they're doing, and this ties into what they should be doing in algebra. You know, you take the second one here, you know, IR, but then, you know, well, I'm pointing at the screen. How dumb is that? All right, never mind.
Well, the point is that we're doing it. Essentially, we're doing it. We did it in equations on the previous page, and then I'm showing here how to divide or multiply both sides by something. But also we have a script.
Mm-hmm.
And so I think that basically I equals V over R, here it is in the script. And what I need to show is that, you know, here's what it looks like as a stated equation. And then here's what it looks like as an example for calculations.
Right.
Yep. And then here's what it looks like in
Implement.
code.
Yeah.
All right. Yeah, that makes sense.
I have that noted. And my cell phone has also been ringing off the hook. So I had better conclude today's workshop.
Now, do we, Andy, do we have that thing with the stepper motors? Is that script out there already? Or you're gonna put it out there for the homework?
Yeah, I'm gonna send you a link to the Servo document that I went through.
Before midnight, late guy.
Around, oh yeah, did you see my last homework?
I was online. I was coding.
Midnight's coming before your midnight.
Yeah.
You know, the thing was, after I hit send there, I thought, oh geez, is somebody's cell phone gonna make a "you've got mail" statement at 3 a.m. because I did that? I take it that didn't happen to you, Ed, but
Oh, no, because I'm used to, my daughter has special needs, so I'm used to the 2 a.m. phone calls.
oh boy, okay.
You know, my fish is not swimming properly in the tank. What should I do? I don't know. You know, so no, that doesn't bother me. And then the years in industry and stuff like that, I just got used to that.
Yeah, but normally what I do is if it's midnight or 1 a.m. or something, I just schedule it so it goes out fairly early in the morning instead.
Last night was a celebration anyway.
Well, nice.
Alright.
I appreciate it. Look forward to seeing it. I appreciate you staying later than normal, Andy, and helping us with these issues. And
Yeah, normally I actually like to wear everybody out and win the battle of attrition, but today I think I'd better jump off.
Jump off. We see Ken still there.
Yeah, and I'm gonna run and tell him to stop recording after we.
Yeah. Okay.
All right then.
I do like the suggestions that were brought up by the others on maybe creating a few of those wrong lessons that students have to follow and troubleshoot, because you're
Oh,
right,
yeah,
Ed,
totally.
is that, you know, if somebody walks into a job and gets a pair of scissors, they expect it to cut. And if it's not cutting, 90% of people wouldn't know what to do. I mean, it's just, you know, so teaching my students to move on into the engineering field, the teachers there tell me that they're the best prepared because they can fix whatever happens. Because we screw things up and have to solve problems. That's the most important thing that I teach them.
Yeah, perfect. I'm completely on board with this.
All right. Have a great day. We'll see you on Friday.
Thank you. We'll see y'all on Friday. Have a good one.
Take care. Have a good day,
everybody.
Bye now.
Yes, I'm leaving the meeting.